So, hello everyone, welcome to the real ultimate seminar for this season. Today we have the opportunity to listen to Antoine Dailly, who is a researcher at the INRAE in France, and he will talk about the Canadian traveling problem on outerplanar graphs.
Yeah. So thank you for the introduction and thank you for having me. This is joint work with all those very nice people. It's a more or less Clermont-Ferrand project, except for Aurélie, who is in Grenoble, and nowadays Pierre is in Grenoble and Zevolod is in Ulm, and I forgot to put the Ulm logo. Sorry about it. So that's, the cold room is perfect because in the hot room this would not make a lot of sense. So this is about Canada, and Canada is very cold. So imagine you're in Canada, you're a Canadian, and you want to travel. You have a graph, a road network with weights on the edges, and you want to reach a given target. Okay, so you say, okay, I will follow the lowest edge. Okay, and here I will keep track of my travel distance. But when I reach this vertex, I learned that it's been snowing a lot and the road is blocked, so I cannot take the red block, like the red blocked edge. Okay, never mind. I will go to another place, and here this road is closed, and this road is closed, and so on. And we discover that the roads are closed when we reach an endpoint, and then we just know everything. If a road was open when we visited the vertex, it will always remain open because it's day now. And if it was blocked, then it will stay blocked because those people cleaning up the snow, they're not very fast. Reindeers or something, I don't know. However, we assume that you can always reach your target. Okay, you always have an open path, and I will explain why later. And the cost of your travel is the total weight of the edges that you traversed, including if you travel several times the same edge, you count it twice, or 3 or 4 times, and so on. This is the Canadian travel problem, and of course, the blocked edges are hidden. Otherwise, this is just a disk problem. And once we have reached the target, we can ask someone who has all the information to give us the optimal distance. And this will help us rate what we paid. As a formal definition, so this is the K Canadian traveler problem, which was introduced, of course, by Greeks. And so you have a weighted graph.
You had snow in Greece.
That's the joke. A weighted graph with 2 vertices, your start and your target, and you have a hidden input, which are K-blocked edges, at most K-blocked edges. And your goal is to go from S to T with the minimum cost. And so in order to grade a strategy, you try to use a ratio between what you traveled and what the optimal distance is when you have the hidden input is not hidden, right? When you have the exact input. And this is called a competitive ratio. So this is a non-line problem because when you walk, you discover new information which remains in your memory, but so you don't have the whole information at the beginning. However, you will notice that the competitive ratio is unbounded even for very simple graphs, so planar of treewidth 2. If you take this graph here, epsilon is very small. You have lots of paths, k plus 1 path, okay, parallel path of weight 1 and epsilon for the second one. Well, your only strategy here is to try one path, and then the opponent blocks you, and you try another path, and the snow blocks you. And so the ratio is 2k because you travel 1, 2, 1, 2, 1, 2, plus 1 plus epsilon, which is the real cost, and the real cost is 1 plus epsilon. So you have this ratio, and you cannot beat it. No strategy can beat that, of course. And this is planar, and this has treewidth 2. And you can even make it unit weighted by just having very long paths and saying, asymptotically, this is good. So yeah, this is quite a hard problem in general. And indeed, it is p-space complete. So why is it p-space? P-space is a class of games and puzzles. And here you can have the snow as the opponent. So you have your strategy as a traveler, and there is this snow guy. He's making the snow fall from the sky or whatever. And I don't know, we don't really have snow in France either.
So what's the decision question?
Can I do it in at most with a ratio at least? I think it's yes, ratio at least at most something. Okay. And actually, there is also another variant somewhere, but I don't remember the exact decision variance. But it's in p-space and p-space hard. And you have lots of variants also that can help to model real problems, so probabilistic, multiple travelers, you can sense remote edges and stuff like that. But most of them are still as hard as the basic problem, and you don't really gain much. You can actually make the ratio terrible, even, for example, if you can sense remote edges by just creating artificially long paths, stuff like that. The greedy strategy, which might be the first we think of. So you go from S to T, you follow a shortest path, and when you're blocked, okay, you compute a new shortest path from X to your target, from where you were blocked to your target. But this can be arbitrarily bad, and this can be shown. I won't show you the construction, but yeah, it can be terrible. However, there are two strategies that reach the ratio. Remember the best K that you could reach, 2K plus 1. And one is called reposition, because what you do is that you follow the shortest path. But when you're blocked, you just go back to the start and you recompute the shortest path. Okay, and if you do that, you can prove that it's 2K plus 1. It has ratio 2K plus 1, so it's okay. And there was then another strategy, which is a comparison, and it's sort of you compare between greedy and the reposition, and you have a weighted ponderation and stuff. It's way more complex, and it has the exact same ratio. So, I mean, worst case ratio, but it's better in some cases than reposition. And you can also have non-deterministic strategies. I don't know much about non-deterministic things and probabilities, but Demain et al. In particular, they have this very nice ratio, way better, of course, than 2K plus 1. But you know that we cannot actually have like better than a K ratio, K plus 1 ratio, even if you're using non-deterministic strategies. And here there is a high probability of something, but again, I mean, probabilities are scary. So don't worry, this will be deterministic. So that's the history. And basically what we were looking at, we are more structural graph people originally. And so we were thinking, okay, so you have unbounded ratio for planar graphs, even of treewidth 2. And you have some graph classes where you have a constant ratio. So trees, of course, because the path is always up, there is always an open path. And in trees, there is always one path. So the ratio is 1. Very nice. Cacti. Cacti is a bit harder. It's basically cycles. Cycles, you have two choices, and one of them is open. So at the worst, you have to do like one full turn, and then you're blocked at the end. So you do the whole turn. And cacti are just the same. You do the same on every cycle you're in. So you have a ratio 3. And in the middle is outerplanar graphs. Outerplanar, they are planar, treewidth 2, but they are way more structured than planar treewidth 2 in general. Okay. So we looked a bit at outerplanar graphs, and actually, the guy who proposed the problem was Pierre Berger, and he worked on this, I think, during his PhD, and he found it's actually a consequence of if you have a bounded number of cuts between S and T, then you can have a good ratio, and this gave him 2 to the power 3/4 K ratio. So this looked like promising. We thought, hey, maybe we can have constant ratio on outerplanar graphs. And our results are the following. For unit weighted, so all edges have weight 1, we have ratio 9. So constant ratio. This is fun. And this means that if you have a bound on the ratio between two weights, then you have 9 times this bound, this ratio here as a ratio, because you just assume that everything is super expensive and you do your strategy for constant ratio for a unit weight. We also have the proof that this is basically the best you can have, the best you can hope for. There is a family where you have this ratio 9, which is reached by any strategy. And for arbitrarily weighted, we actually show that it's impossible. Like the ratio is not constant. You have this lower bound, which is ln of k divided by ln of k. I don't know the exact details of this. This is caused by a Lambert function or something. Very scary. I will not try to explain it too much, but this comes from computations. Okay. And so non-constant ratio on weighted outerplanar graphs. Okay. If you have any question at any point, of course, you feel free to ask and interrupt. So I'm going to explain this, then that, then this. Okay. So first, let's prove that no strategy can achieve ratio less than 9 in outerplanar graphs. unit-weighted outerplanar graph. So this comes from shells and cows. And again, I don't see the relationship with Canada, but maybe there are cows in Canada, I think, maybe. Okay, so our graph, our worst case graph is like this, okay, it's a shell. You start on the left and you want to reach the end here. And you have all chords here, all the chords on both sides. So basically the idea is you try to go there and the opponent just blocks you. So you try the other side and it blocks you, and in the end he will run out of blocks, and then you can reach the target. And actually what you can show is that this is equivalent to a famous problem, which is the co-path problem. And in the co-path problem, you are in a line, so you start at 0, for example, and you have a co somewhere on the line, either in the positive or in the negative, real. And you need to find your co, but you don't want to travel too much. And the base strategy is you go on the one direction, you go 1. In the other direction, you go 2. Then in the other direction, you go 4 from the origin. And in the other direction, you go 8 from the origin. And in the other direction, and so on. And then at the end, you will find it. And it was proved that you cannot be better than this. And this has ratio 9. This comes from a sum of powers of 2. And yes, so this was proved for the co-path problem, and we actually reproved it in another way using some very complicated metrics things, which I will not try to explain because I didn't understand this part. But yeah, so this is the worst case here, a very simple graph. However, we proved that actually you can have ratio 9 on any outerplanar graphs, even like, and we have a very nice strategy for this. And basically, the idea is you decompose the graph by managing the articulation points, and then you use this 2, 4, 8, and so on the 2 connected parts. And you have to manage chords within your 2 connected parts. And then you use an induction, and this allows you to iterate. And the idea is that when you're in your 2 connected parts, this forms like a big cycle thing, and you can like using the chords may be beneficial, but you have to understand how it's beneficial or not. So first, articulation point, this is a technical lemma. Don't worry about it too much. What it means is that if I have like a graph, any graph actually, this is not a problem. I mean, it needs to be a monotone family and whatever. Basically, if you can win on graphs with no articulation points in the family, then you can win on the family with the same ratio. How do you do this? You remove the components that are completely useless because they will never be on the shortest path between your start and your target, and actually you will have to go through your target or it's fully decomposed, like separated from your path. Those are useless, just remove them. And then for every articulation point, you just cut and you reason on each part. That's it. And if you apply your strategy on this, this, and this, the ratio you will have on the whole graph is the worst of the ratio you have on your subgroups, okay, on your intermediate graphs. So this is easy. And this works actually on any monotone family, so not only outerplanar, but it's useful for us. But it can be useful for other classes maybe. And now let's look at the balancing. How do we work on this? So we have our 2 connected components. Right. We have 2 sides, and we just give one of them is up and one of them is low, down. It's okay. It doesn't really matter. And then you have vertical chords. They are linking the 2 opposite sides, and the horizontal chord they are linking 2 vertices on the same side. And one good observation is if you see an open horizontal chord, you take it and you remove what's below, right? Because now this vertex here, it's useless. It doesn't matter. And if you're blocked on one side, then you can basically you switch to the other side and you find the first time where you re-become a 2 connected component, and you reapply the simplification along the way. This is actually a bit you need to manage it to show that you still have the good ratio and so on, but this works pretty well. And now let's look at the exponential balancing. So what's interesting here is that the exponential balancing in itself works, but to prove that it gives ratio 9 and not 15. And no, it was not 15, it was 13 or something. You need to do some counterintuitive things. You need to spend a bit more so that you can learn and then use information for the induction. So as I said, you give yourself a budget and you work on one side. If you don't find T, okay, you go back to the start and you find yourself a budget, you double your budget, and so on, okay? And you discover things. You skip horizontal chords and you use horizontal chords and so on. Now, when you have several ways where you can encounter a vertical chord, okay? So the first is when you're catching up. So here I am catching up on the lower side to the budget of the upper side that I use on the upper side. If I find a vertical chord here and it was not found above, then it goes necessarily further. So it's very useful now because I know that every shortest path from S to T will go through this vertex U. Right? And so this means that I can just take this blue thing and iterate, and now U is my new start. There is another case, it's when you are exploring further than the previous budget. So than your previous budget on this side. So you know that you go further, okay, on the other side. But you don't know, maybe this is still not very good because here you are at distance 1, 2, 3, 4, 5, 6, 7. But on top, you don't know what is the distance to S, right? It is more than 4, but it can be less than 7. And so what you have to do is to go to the other side and you walk back, okay? And you give yourself a back budget, which is, of course, the difference between what you explored here and your previous budget on the other side. And you explore back. And now you have two cases. Either you don't reach an already explored vertex, in which case you know that the shortest path goes from S to T goes through U, and you can iterate like this. But if you find it, then you know that the shortest path from S to T goes through V. And so you iterate, but your starting point is V. And what's funny is that it doesn't really change anything because you may say, oh, but this just changed by 1. But actually, we found that if you just try to plug it without this information, you try to plug your things into your induction, you can't find 9. You find like 13 or something because you have a max somewhere and you are forced to take the highest, and it just breaks down the inductive part. And sometimes you will find that U and V are at the exact same distance, in which case, okay, you just say, I will use it to switch sides, but I still consider that S is my starting point. Again, this is to have inequalities make sense when you do the induction. So this is fun because in a sense, this is useless to go back because you don't progress, but this is just like to help the numbers go the right way. And so why does it work? You have this very nice automata-like thing. When you are here, you are on one side and you explore the distance D, and you are explore distance D on the other side. And then you can go D further because of the budget doubling. So this is this, and then you go to, if you don't find T or in a vertical chord and so on, you go to the other, you switch back to the other side, and now you explore again D here, and you find yourself in the above thing, but with D equals to D. You update your value. And what's funny is that you can very easily see that this skips the ratio 5 on top, 6 here, and 9 on the bottom. And basically, the going back within the leftover budget happens only here. And this means that you have margins. You can allow you have a bit more to spend. You have saved up quite a bit on the ratio 9. So you can explore a bit further back, and this is why this works. So that's it, right? Unweighted graphs, outerplanar graphs, fun ones. Now, you go, when we were thinking, oh, this works for unweighted, this works for bounded stretch. Now, what is blocking us? And we actually found that you cannot have constant ratio for weighted, arbitrarily weighted outerplanar graphs. So this means that the ratio can be very, very large. We will actually use those very, very cheap edges at some point. So you have this ratio here, e to the power, this function w of ln of k over 2 minus 1, which asymptotically grows like this. Okay, I will not go into the details here because this analysis, this is very scary to me. The proof idea is very basic. You just build a family, hi, by induction, such that for any small thing, small integer, you cannot have, you have this ratio here, I plus 1 minus this epsilon, on the graph hi for any strategy. And you don't use too many blocked edges. You use this number of blocked edges. This is very small, right? I plus 1 factorial squared, very small number. Should be all right. And you know that you will actually travel a lot. I plus 1 factorial. So yes, this is a very large family, family that grows very fast. The first graph is this one here, very basic. This is H0 or H1 maybe. It's probably H1. So you go from S to T here. You have this weight, this chord is of size 2, and you have 1 and this epsilon star, okay, which is very, very small. And of course, if you go above, the opponent just says, oh, but the path below was open. Why didn't you take it? But if you go below, the opponent blocks this edge. And now you have to pay 2, like 3 more. And so here you have 2, and the real cost was 1 plus epsilon, so this is ratio 2. So 1 plus 1. And if you go below, you pay 1, 2, 4, but the real price was 2, so again, ratio is 2.
Sorry, so in this case, I would imagine that when I'm standing in S, I already see that this edge is blocked. So
No,
I understand you can innovate that like
this one is open always, but this one is blocked.
yeah,
They
but
will
like
block. No,
okay.
no, this you don't see. You just see the endpoints. You just see all the edges where you are at of every vertex you visit. Okay, not those at a given distance. So yeah, you could choose to just go from S to T, but then what if this was? This is very cheap, enticing. This is how you build your graph from your previous graph, okay? So you take your starting vertex here, and you have your target here, and this long chord here is very expensive. It's the cost that we want to say. It's the I plus 1 factorial, and it's always open. It will always be open. This is just to say, this is like the opponent taunting you, take it, take it. And then you add lots and lots and lots and lots of copies of your previous graph, hi minus 1. And all of those, the terminal vertex is linked to the real terminal vertex with a very cheap chord. And this is the opponent enticing you by saying, hey, if you can traverse this graph, maybe this chord here is open. Wouldn't this be nice? Ah, this is closed. Sorry, but maybe the next one is open. Don't worry about it. And you add like this many copies. That's a lot. And this is an example of H2. So yeah, those grow large very, very, very fast. Okay. So this was H1, and you just have like lots of copies. Okay, and there are basically 4 kinds of strategies that you can have. So now, basically, the idea, of course, when you prove a competitive ratio is if you say, okay, I'm looking at every possible strategy, and I say, then I fix one. I say, this will be my strategy, and I look, can the opponent block me? Can the opponent make me pay more? So basically, the traveler chooses their strategy, and then the opponent chooses their blocking strategy according to the knowledge of the strategy of the traveler. So this is a reminder, we want to look for this I plus 1 ratio, and you have, in particular, this here as the travel distance that will be I plus 1 factorial. So 4 kinds of strategies for the traveler. The first is to just cross SI. Yeah, okay, whatever, I will pay. But then the opponent blocks nothing, and the real cost is super cheap because it's taking the epsilon star edge and then the other epsilon star edge. So it was very, very, very cheap. So this is a terrible strategy. Don't do this. Try to explore a little. Don't worry. Second type of strategy is to say, okay, I will go to T by going below. I will, yeah.
In the H0 graph, the minimum cost was like 1.
Yes, it's a 1 plus 2 epsilon star. Sorry. I forgot the 1 plus here. Again, nicely said. I noticed it, but I said nothing. Yeah, don't worry. You're too attentive. Okay, so second strategy here is to go, you try to reach out to the end, right? You say, okay, I will, whatever it costs me, I will go towards the end. And then I will go, if I'm blocked, then I have to go back and take this last chord, of course. Then the opponent can just block all the epsilon star edges to T, which he can because there are not that many of them, less than I plus 1 factorial square. And so the ratio is like the sum I plus 1. If you want to read the computations, you can. Do you want to read them? Okay. And yeah, basically this comes from the fact that you will travel for each of the graphs in between, you will travel the cost si minus 1, because you say I will try to go as far as possible. So you just take the S1, then chord, then the S1, S2 chord, then the S2, S2, 3, which has a cost of S minus 1, and you pay this n times. You just try to go as fast as possible to the end. This is very costly. Third kind of strategy is to explore very deep below, but try to save up on each hi minus 1. Okay. So you try to weasel out when you go into a hi minus 1, you try to do this kind of strategies where you save up a lot and you try to gain on the ratio. And then at some point you say, oh, okay, no, this is too far. It's not worth it. You go back and you just take your loss. So here the opponent has enough blockages to make traversing each copy costly. And actually this comes from the fact that you say, okay, I will travel a given time here, D2, and this is when D2 is large, like you go deep inside below. And you know that you will pay the ratio of the I minus 1 times the distance that you travel here. And so again, lots of equations, and you end up with your previous ratio plus 1, and your previous ratio was I minus 1 plus 1. This is I, so I plus 1. Nice. And the fourth case, is when you go just a little bit below. And it's very similar, it's just that the computation is completely different and way more complex. It takes like 1 page. And because you have this kind of ratio, but in the end it works, right? It works with computation magic. It's not really hard, it's just technical, like long and technical. It's technically slightly different because of those computations, but it's of course the same strategy for the opponent. Just make it very costly. Yeah. Okay, and of course cut the epsilon star cost, because otherwise it's very cheap to go there. And so in the end, what you do is that you say, okay, I allow myself k block edges. So this proves basically that on the family hi, the competitive ratio is always at least I plus 1 plus a small epsilon. And you block not too many edges. And so when you say I allow k blocked edges, I choose my I wisely so that I can have this many blocked edges. And then I can have a competitive ratio which is greater than this function. And this comes from the resolving some equation here, exponential equation. Because this W function is a reverse of some x exponent e power x or something. And so asymptotically, what matters, is that analysis people show that asymptotically this grows as much as this and as most this. Okay. What's interesting here is that this makes us think that the log k here would be the good solution for the weighted outerplanar graphs. Maybe there is a worse family, but we couldn't really find one, and we actually think that we are trying to develop a strategy that works in ratio log-K. But of course, we can be mistaken, because at first we were thinking, this could be I think we thought this could be lower than this, but then we found this graph family, and yeah, so you never know. Maybe this will become larger. I don't really see this kind of construction, how you can really make it worse, worse in an asymptotic kind of way, in a big O kind of way. All right. So if I summarize, what we did was to split the outerplanar graphs. We have the unit weighted and bounded ratio between the weights and so on, which is in constant ratio. And the arbitrarily weighted are in unbounded ratio, and we have a lower bound, which is actually quite strong, and an upper bound, which is quite strong also. So they are logarithmic and polynomial, square root polynomial. So this asks lots of this. This kind of drawing just suggests questions, right? It's, do you have another family of outerplanar unit weighted where you have a constant ratio, which are a bit more complex than cacti? Do we have something where, because for cacti, weights don't matter. So do we have something between cacti and outerplanar where you are in constant ratio, but the weights are arbitrary? And of course, what of P outerplanar graphs. So it's, I think they can be drawn in a surface of genus P with everything outside. I don't remember the exact definition. It's between outerplanar and planar treewidth too. That's what matters. It's a more complex family. And again, this is open. And of course, what is a true bound for outerplanar? What is a true ratio? And we think it's log K. You can race us if you want to, but we would prefer not. It's okay otherwise. Yeah, I think this one here is quite intriguing because what is below outerplanar, but slightly more complex than cacti and could have constant ratio? I don't know, maybe there is a good condition here to flow. All right. So this concludes the talk. Thank you for your attention.
Thank you, Antoine. Do we have any questions?
There will be a chance, like if in every two-connected component you have like constant feedback edge subnumber, would that make sense?
That would be nice. That may help. We haven't looked at the feedback edge, so maybe this is a good opportunity here. Maybe because now you can, because you're almost a tree, right?
Yeah, for cacti it's one for
yes.
every two connected components. Yes. So if you have 2 or 3,
yes, bounded number, like say k, a function of k, for example, could be nice. Yeah, that's something to keep in mind. Thanks.
Yeah.
So, is there anything known about when the opponent cannot block like edges that are like at the same vertex? For example, what if I insist that the edge is blocked for my matching, for example? Because it seems to me that every time the strategy is like, oh, you can reach T or you can reach T, so then I block almost every edge to T. So
I probably can just subdivide a bit more, and then for example, like.
Yeah, I see. So
this, I transform this into my counterexample into this. So just sub here. And I block this one, and this one is a negligible cost. Mm-hmm. Probably this works for transforming most counterexamples. Maybe you lose a bit of structure, but for example, for the planar of treewidth 2, you just can do it. You can do it this way. But maybe this can help for some weird way if you add some structure, maybe with the feedback edge number, bounded feedback edge number or something. Nah. Because it's the same.
And maybe for another idea, it's not the same as the feedback edge number, but what about bounding the number of cycles each edge?
Actually, it was less. It was less cycles than ST cuts that were really strong with this, because you can have useless cycles. So.
Oh yeah, what I'm saying is that like in cacti, every edge is on at most one cycle. But if
yeah,
is in at most 2 cycles.
I think, yeah. No idea. Isn't it feedback edge? This looks like feedback edge number. Is it equivalent? I don't know.
I don't know whether equivalent. I expect that one of them is bounded than the others.
I mean, if you bound this, you bound the feedback. No, if you bound the feedback edge number, then you bound the number of cycles. The reverse is not necessarily true, I think. You can have like lots of very small cycles, very annoying, but very easy to cut. No, I don't. But yes, this is similar. But cycles in and on themselves, you can just add useless cycles and stuff like
that. Yeah, I was wondering. As your example was there, I was thinking that okay, while you're having bigger graph, you need a bigger number of blocked edges. So what if we completely fix the number of blocked edges and have a huge graph? Does this there is a strategy that may?
I think there is a strategy because you can
explore a bit.
Yeah, you can basically. I don't remember, but I think it was you had an FPT thing probably because you can just try the shortest path, and then at some point the opponent cannot block you anymore. So unless they really all join at a very dense cluster of the side, the bound of the thing, and then you just go there and you try to exploit. So either it doesn't really help or it becomes really easy. I think. But yeah, you kind of, since you evaluate for unbounded, we consider that you have the K that can evolve. So
I have a question. Two. First of all, the unique weighted outer planar graphs. If you get rid of the shells,
Yes.
do you also have another subgroup of outer planar graphs that require 9?
We didn't look for one. We haven't looked for one.
So
But maybe by shells, but also shells as minors.
Something.
No, we didn't look for it.
And the other question, are you aware of any work on this thing, on a variation where you would have more travelers and it's sufficient that one of them reaches the terminal?
Yeah. Mm.
And still one adversary.
What is the first one is home? Multiple travelers was a part. No, but it passed very fast. It had been studied. I haven't read the paper. It had been studied. I don't think it helps much. It depends also on the communication between them, but it doesn't help that much. And also how you count. Do they move at the same time or do you count the sums? If you count the sum, it doesn't really help. But otherwise, it's.
I would count the minimum between them, for example.
Yeah, I don't remember the results here. I just read very quickly.
Because you mean like multiple travelers in one?
Yes,
Yeah.
one. But the multiple travelers also move at the same time.
Yes.
They're synchronous.
But
they can
in
explore
case that
more.
you give me multiple travelers, multiple targets.
If both of them are multiple, then it comes back to this problem.
Yeah. And actually, there is a variant we consider it as a game where you have one traveler and one blocker, but the blocker can only block one edge on their turn. But they're not limited to blocking it where the traveler can see it, and the traveler sees what is blocked. This is P-Space Complete also, of course. So it's a game version. It's called it Nemesis. It's Greek again. Back to them.
Are there any other questions?
Just clarify, at the end you mentioned outerplanar graphs. You said that it's
No, don't remember the definition.
Yeah, it's the outerplanar on higher genus. Is it the same as having like k layers, or is it different?
Honestly, it's a structure thing, and I was like,
Yes,
this also with you. I'm surprised.
Yes, so perhaps like k outerplanar graphs, but essentially it's like so zero outerplanar is like outerplanar, and then you have
Yes, this is which we cannot use k because k is the number of
yes.
P is it's yes. It's the standard k outerplanar, but k is already used here. Actually, maybe on k outerplanar with a function of k blockage. I don't know.
Maybe let's thank the speaker again.
Thanks a lot.